Tonight, we're going to explore something that will fundamentally break your understanding of reality. We're going to discover the point where distance itself stops making sense. You think you understand what far away means. You know how long it takes to drive to work, how many miles separate continents, maybe even how far the moon is. But here's what almost nobody realizes. There's a distance in the universe, a boundary you can never cross, where the very concept of how far becomes meaningless, where asking how many miles away is that galaxy has no coherent answer, where objects exist that are simultaneously getting closer and impossibly farther at the same time. By the end of this journey, you'll never think about space, about distance, about the universe the same way again. Before we dive into this, if you find these kinds of deep explorations fascinating, a quick like or subscribe really helps the channel grow. It's a small gesture, but it makes a huge difference for me. Now, let's begin. Let's start with something you think you understand perfectly. Distance. You know what distance means. You've lived with it your entire life. The kitchen is 20 feet from the bedroom. The grocery store is 2 miles down the road. Your parents live 300 miles away. These numbers mean something to you. They translate into time, into effort, into experience. A 2-mile drive takes about 5 minutes. A 300-mile trip takes a few hours. Distance is concrete. Distance is real. Distance is something you can measure with a ruler, calculate with a map, feel in your legs after a long walk. This intuitive understanding of distance served humanity well for most of our existence. When our ancestors needed to find water, they understood that the river was a certain distance away. When they hunted, they tracked animals across distances they could estimate by eye. When they built cities, they measured plots of land, laid out streets, calculated how far the wall should extend. Distance was simple. Distance was obvious. Distance just was. Even in the ancient world, humans tried to measure distances beyond their immediate surroundings. Around 270 BCE, a Greek philosopher named Aristarchus of Samos attempted something remarkable. He tried to measure the distance to the sun and moon using nothing but geometry and careful observation. During a half moon, he reasoned, the sun, moon, and Earth form a right triangle. By measuring the angle between the sun and moon in the sky, he could calculate the relative distances. His measurements were imprecise. He concluded the sun was about 20 times farther than the moon, when the actual ratio is closer to 400. But the method was sound. For the first time, a human being had tried to measure cosmic distances using mathematics. The idea that the heavens could be measured, that distance applied to celestial objects just as it did to earthly ones, was revolutionary. A century later, Eratosthenes calculated the circumference of the Earth by comparing shadow lengths in 2 different cities at the same time of day. He knew that at noon on the summer solstice, the sun shone directly down a well in Siene, casting no shadow. But in Alexandria, about 800 kilometers north, a vertical stick cast a measurable shadow at the same moment. By measuring that shadow's angle and knowing the distance between the cities, he calculated Earth's circumference. He got remarkably close to the correct answer, within a few percent of the modern value. These ancient thinkers established something profound. Distance was universal. The same principles that measured a farmer's field could measure the Earth itself, and perhaps even the cosmos beyond. The universe, they believed, was measurable. Distance meant the same thing whether you were measuring the length of a room or the span between Earth and the heavens. This assumption would hold for over 2,000 years. As technology advanced, our ability to measure distance grew more sophisticated. Trains covered hundreds of miles, planes crossed thousands. We developed precise instruments to measure distances with extraordinary accuracy. Surveyors could determine the exact distance between 2 points on opposite sides of a continent. Ships navigated across oceans using careful calculations of position and distance. The world grew smaller, not because it changed, but because we could measure and traverse it with increasing precision. Astronomers extended these measurements into space. They learned to measure the distance to the moon by bouncing radar signals off its surface and timing how long they took to return. They calculated the distances to nearby stars using parallax, the slight shift in a star's apparent position as Earth moves around the Sun. Each advancement confirmed what seemed obvious. Distance was a straightforward property of space. It was the amount of emptiness between two things. Nothing more, nothing less. But then something changed. In the late 19th century and early 20th century, physicists began discovering something deeply troubling about the universe. They found that distance, this concept we thought we understood completely, this foundation of geometry and navigation and everyday life, was far stranger than anyone had imagined. They found that at cosmic scales, distance begins to behave in ways that defy common sense. And at the largest scales of all, distance essentially stops meaning anything. To understand why, we need to start with light. Light travels at approximately 299,792 kilometers per second. In more familiar terms, that's about 186,000 miles per second. This speed, often rounded to 300,000 kilometers per second, is the fastest speed possible in the universe. Nothing can travel faster. Not rockets, not signals, not information of any kind. This isn't a technological limitation that we might someday overcome. It's a fundamental law built into the fabric of reality itself. This speed limit was first established by Albert Einstein in his special theory of relativity in 1905. Einstein showed that as any object with mass approaches the speed of light, its mass effectively increases, requiring more and more energy to accelerate it further. To actually reach the speed of light would require infinite energy, which is impossible. The speed of light isn't just very fast, it's the ultimate cosmic speed limit, a barrier that cannot be crossed by anything with mass. Only massless particles, like photons, which are particles of light, can travel at this speed. And they must always travel at this speed. Photons cannot slow down or speed up. From the moment they're created to the moment they're absorbed, they travel at exactly the speed of light through empty space. This constancy is itself remarkable. Unlike every other speed we encounter, the speed of light doesn't depend on how fast you're moving when you measure it. Whether you're standing still or traveling at half the speed of light yourself, you'll always measure light moving at exactly the same speed. This strange fact was one of the key insights that led Einstein to his revolutionary theory. Now, 300,000 kilometers per second sounds incredibly fast. and it is fast by any human standard. Light can circle the entire Earth about 7.5 times in a single second. It can travel from the Moon to Earth in about 1.3 seconds. In the time it takes you to blink, light has traveled about 30,000 kilometers. By everyday measures, light is essentially instantaneous. When you turn on a lamp in a dark room, the light reaches your eyes so quickly that you perceive it as happening instantly. When you look at someone across the room, the light reflecting off their face reaches you in a few billionths of a second. For all practical purposes in daily life, light might as well travel infinitely fast. The delay is so small as to be completely undetectable by human senses. But here's where things start to get interesting. The universe is big. Really incomprehensibly big. And when you're dealing with cosmic distances, even the speed of light starts to seem slow. The Sun is about 150 million kilometers from Earth. That's 93 million miles. Light from the Sun, traveling at 300,000 kilometers per second, takes about 8 minutes and 20 seconds to reach Earth. This means that when you look at the Sun, you're not seeing it as it is right now. You're seeing it as it was 8 minutes ago. If the Sun suddenly vanished this instant, we wouldn't know for over 8 minutes. We'd keep seeing sunlight, feeling its warmth, completely unaware that our star had disappeared. This is a strange thought, but you can still wrap your head around it. 8 minutes isn't that long. The delay is real but manageable. We're still basically seeing the Sun in real time, give or take. You could have a conversation with someone on the Sun, if such a thing were possible, with only an 8-minute delay each way. Slow, but workable. But this delay has real consequences that we deal with every day, even if most people don't realize it. Consider the robotic spacecraft we've sent to explore other planets. When NASA operates rovers on Mars, there's always a communication delay because Mars is so far away. At its closest approach, when Earth and Mars are on the same side of the Sun, Mars is about 55 million kilometers away. Light and radio signals take roughly 3 minutes to cross that distance. At its farthest, when Earth and Mars are on opposite sides of the Sun, the distance stretches to about 400 million kilometers. Signals take over 22 minutes each way. This means engineers on Earth cannot drive a Mars rover the way you drive a remote-controlled car. The delay is too long. If the rover encountered an obstacle and you tried to steer around it in real time, by the time you saw the obstacle, sent a command, and the command arrived, over 44 minutes would have passed at maximum distance. The rover would have long since crashed. Instead, mission planners must program entire sequences of commands in advance. They analyze images from previous days, plan a careful route, write detailed instructions, send those instructions to Mars, and then wait. If something goes wrong, if the rover encounters an unexpected rock or gets stuck in sand, the engineers can't react immediately. They must wait for the problem report to reach Earth, analyze the situation, devise a solution, write new commands, send them, and wait again for execution. A problem that might take seconds to solve with a remote-controlled car in your backyard can take hours or even days to solve on Mars. The Perseverance rover, which landed on Mars in 2021, must make many decisions autonomously because of this delay. Its software can identify hazards and navigate around them without waiting for instructions from Earth. It has to be semi-independent, a robot that can think for itself, because the speed of light makes real-time control impossible. This is the speed of light making itself felt in practical terms. 3 minutes to 22 minutes of delay doesn't sound like much, but it fundamentally changes how we interact with anything at that distance. Real-time control becomes impossible. Communication becomes a slow exchange of messages rather than a conversation. The finite speed of light transforms the way we must operate. And Mars is close. It's our neighboring planet, practically next door in cosmic terms. When we sent the Voyager spacecraft to the outer planets, the delays grew much longer. By the time Voyager 2 reached Neptune in 1989, signals took over 4 hours each way. Command sent in the morning wouldn't arrive until afternoon. Confirmation that the commands had executed wouldn't come back until evening. The spacecraft had to be programmed to handle the entire Neptune encounter essentially on its own, with human controllers unable to intervene in real time. Today, Voyager 1 is over 23 billion kilometers from Earth. Signals take more than 21 hours to reach it. A command sent this morning won't arrive until tomorrow. The spacecraft, launched in 1977, is so far away that it's essentially operating in the past from our perspective. By the time we learn what it's doing, it has already moved on to doing something else. Things get far stranger as we look beyond our solar system. The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri system. It's about 4.24 light years away. A light year is the distance light travels in 1 year, which works out to approximately 9.46 trillion kilometers, or about 5.88 trillion miles. So Proxima Centauri is roughly 40 trillion kilometers from Earth. When you look at Proxima Centauri, you're seeing light that left that star 4.24 years ago. The star you're seeing is the star as it existed when you were 4 years younger. If Proxima Centauri exploded right now, we wouldn't see the explosion until 4.24 years from now. For over 4 years, we'd keep seeing the star shining peacefully, completely unaware of its destruction. If we ever sent a spacecraft to Proxima Centauri, communication would be agonizingly slow. A message sent to the spacecraft would take 4.24 years to arrive. The reply would take another 4.24 years to come back. A single exchange of information would take nearly 8.5 years. You could ask a question and your children might be the ones to hear the answer. This is where distance starts to get weird. Because when we talk about the distance to Proxima Centauri, what do we actually mean? Do we mean the distance between Earth's current position and where Proxima Centauri is right now? But we don't know where it is right now. We only know where it was 4.24 years ago. The light we're receiving is old information. Proxima Centauri is actually moving through space relative to us. It's approaching the solar system at about 22 kilometers per second. In the 4.24 years since the light we see tonight left that star, it has moved about 3 billion kilometers closer. The star isn't quite where it appears to be. It's slightly closer now than the image we see suggests. This might seem like a technicality, but it becomes profoundly important as we look at larger distances. Sirius, the brightest star in the night sky, is about 8.6 light years away. The light you see from Sirius tonight left that star about 8.5 years ago. You're looking at Sirius as it was when you were nearly a decade younger. If you're 20 years old, you're seeing Sirius as it was when you were 11. If you're 40, you're seeing it as it was when you were in your early 30s. The star in the sky is a window into the past. Polaris, the North Star, is about 430 light years away. The light entering your eyes when you look at Polaris tonight began its journey around the year 1595. Shakespeare was writing his early plays. The first permanent English settlements in North America were still years in the future. That light has been traveling through the void of space for over 4 centuries, finally arriving at Earth tonight. Betelgeuse, the famous red supergiant in the constellation Orion, is about 550 light years away. The light from Betelgeuse that enters your eyes tonight began its journey around the year 1474. That was during the Italian Renaissance, before Columbus sailed to the Americas, when Leonardo da Vinci was 22 years old. The light has been traveling through space ever since, finally arriving at Earth tonight. Betelgeuse is a dying star. It's massive, about 20 times the mass of the Sun, and it has exhausted most of its fuel. Someday, perhaps soon in astronomical terms, it will explode as a supernova. When it does, it will briefly shine as bright as the full moon, visible even during the day. But here's the unsettling truth. Betelgeuse could have already exploded. The supernova might have happened centuries ago, in the year 1500 or 1600 or even later. But we wouldn't know yet. We'd keep seeing the star as it was 550 years ago, waiting for the light carrying news of its death to finally reach us. The explosion might already have happened. The light just hasn't arrived. This creates a fundamental problem for understanding distance in the universe. We can never see anything as it is right now. We only see things as they were when the light left them. The farther away something is, the further into the past we're looking. Distance and time have become inseparable. This connection between distance and time isn't just an observational inconvenience, it's a fundamental feature of reality. Einstein's theory of special relativity showed that space and time are not separate things. They're woven together into a single 4-dimensional fabric called space-time. You cannot fully describe where something is without also describing when it is. Position in space and position in time are connected in ways that classical physics never anticipated. One of the most surprising consequences of this connection is that there is no universal now. In our everyday experience, we assume that now is a universal moment shared by everyone and everything. Right now, at this instant, the moon exists, the sun exists, Proxima Centauri exists. Everything in the universe shares this present moment with us. But relativity shows this isn't true. The concept of simultaneity of 2 events happening at the same time depends on your motion. 2 events that happen at the same time for one observer might happen at different times for another observer moving relative to the first. This isn't an illusion or a measurement error. It's a genuine feature of space-time. Imagine 2 lightning bolts striking the ground at the same moment, one to your left and one to your right, each the same distance away. You see the flashes simultaneously and conclude they happened at the same time. but someone riding past you on a fast train would see things differently. Because they're moving toward one strike and away from the other, the light from each strike reaches them at different times. They would conclude the strikes happened at different moments. You might think this is just a matter of perception, that the strikes really did happen simultaneously and the train passenger is simply mistaken. But relativity tells us there is no really about it. Both perspectives are equally valid. Neither observer's judgment of simultaneity is more correct than the other's. Simultaneity is relative, not absolute. What this means is that there is no single right now that applies to the entire universe. The question, what is happening on Proxima Centauri right now, doesn't have a definitive answer. It depends on your frame of reference. Different observers, moving at different speeds, would disagree about what now means for that distant star. This breakdown of universal simultaneity is the first crack in our intuitive understanding of distance. When we ask how far away is Proxima Centauri, we're implicitly assuming that there's a now when both Earth and Proxima Centauri exist simultaneously, and we're measuring the space between them at that moment. But that assumption doesn't hold up to scrutiny. There is no universal now. The distance we measure depends on conventions we choose, not on some objective fact about the universe. For relatively nearby objects, within our solar system or even within a few dozen light years, these issues don't cause major problems. The differences between different ways of measuring distance are small enough to be negligible. We can treat distance as we always have, and the answers we get are close enough to be useful. But as we look deeper into the universe, as we examine galaxies millions or billions of light years away, these conceptual problems grow. And eventually, they don't just cause minor complications. They cause the entire concept of distance to break down. Let me give you a sense of the scales involved. The Andromeda Galaxy is about 2.5 million light years away. This means the light we see from Andromeda left that galaxy 2.5 million years ago. When that light began its journey, early human ancestors were just beginning to use stone tools in Africa. Homo sapiens didn't exist yet. Our species, with all its history and civilization and technology, didn't even exist when that light began traveling. The entire history of modern humanity has unfolded while that light was crossing the void between galaxies. When you look at Andromeda, you're not seeing a galaxy in the present. You're seeing a galaxy as it existed in the deep past. The Andromeda you see tonight is not the Andromeda that exists right now. Stars have been born and died in that galaxy since the light left. Planets have formed. Perhaps civilizations have risen and fallen. Whatever is happening in Andromeda now is completely unknown to us and will remain unknown for another 2.5 million years when the light from those events finally reaches Earth. By the time we could ever reach Andromeda, assuming we could travel at the speed of light, which we cannot, 2.5 million years would have passed. The galaxy would have changed dramatically. Any civilizations that might exist there would be completely different from whatever was there when we set out. And Andromeda is relatively close. It's one of our nearest galactic neighbors. It's close enough that it's gravitationally bound to the Milky Way. The two galaxies are actually falling toward each other and will merge in about 4.5 billion years. In cosmic terms, Andromeda is right next door. The Virgo cluster, A collection of about 1,000 to 2,000 galaxies is about 54 million light-years away. The light from galaxies in the Virgo cluster left during the Eocene epoch, when Earth was populated by early primates, when the continents were in different positions, when the climate was far warmer than today. Dinosaurs had been extinct for about 10 million years. Our distant ancestors were small, tree-dwelling creatures. The world was unrecognizable. Beyond the Virgo cluster, the distances grow even more staggering. The Coma cluster of galaxies is about 320 million light-years away. The light we receive from it left when fish were first crawling onto land, when life was beginning its great migration from the oceans to the continents. Life on Earth had not yet developed lungs in the modern sense. The transition to terrestrial existence was just beginning. When we observe galaxies billions of light years away, we're seeing them as they were billions of years ago. We're looking back in time to eras when the universe was young, when galaxies were still forming, when the conditions everywhere were different from what they are today. A galaxy 10 billion light years away appears to us as it was 10 billion years ago. The Earth didn't exist yet. The sun hadn't formed. We're seeing the universe as it was before our solar system came into being. The most distant light we can detect, the cosmic microwave background radiation, was emitted about 380,000 years after the Big Bang, roughly 13.8 billion years ago. When we observe this radiation, we're seeing the universe as it was when it was less than 1% of its current age. The universe was a hot, dense plasma. No stars existed yet. No galaxies. Just a glowing fog of matter and energy. But here's something that seems impossible. The matter that emitted that ancient light is now about 46 billion light years away. The universe is only 13.8 billion years old. How can something be 46 billion light years away in a universe that has only existed for 13.8 billion years? This apparent paradox is where distance truly begins to fall apart, and understanding it requires grasping something even stranger than the finite speed of light. It requires understanding that space itself is not standing still. The universe is expanding, not like a balloon being inflated into some larger space, but in a far more fundamental way. Space itself is stretching. The fabric of space-time is growing, carrying everything with it. The galaxies are not moving through space away from each other. The space between them is increasing. There is literally more space today than there was yesterday, more yesterday than the day before, more 1 billion years ago than 2 billion years ago. This expansion doesn't just complicate our understanding of distance, it eventually makes the very concept meaningless for large enough scales. The concept of distance that served humanity so well for millennia, from Aristarchus measuring the heavens with geometry to engineers calculating light speed delays for Mars rovers, begins to crumble when applied to the cosmos. The simple idea that distance is just the space between two things, an idea that seemed as solid as the ground beneath our feet, turns out to be an approximation that fails at the largest scales. We haven't even gotten to the hard part yet. The hard part is understanding how the expansion of space transforms distance from a straightforward measurement into something far more slippery. How the universe can contain objects that are, by some measures, farther away than light could have traveled since the beginning of time. how there are regions of space we can see right now that we will never be able to reach or communicate with, no matter how long we wait or how fast we travel. The simple question, how far away is that, has no simple answer when asked about distant galaxies. The question assumes a framework that doesn't apply to the cosmos. It assumes space is static, that distance is unambiguous, that measuring separation is straightforward. None of these assumptions hold. Let's explore how space expands and watch the concept of distance dissolve before our eyes. Because once you understand the expansion of the universe, you'll begin to see why asking how far away is that galaxy might not even be a sensible question. We've established that looking into space means looking into the past. The farther away something is, the older the light we receive. But there's something even stranger happening. The universe isn't standing still while that light travels. Space itself is stretching, growing, expanding. And this expansion transforms distance from a simple measurement into something far more complicated. The discovery that the universe is expanding was one of the most profound scientific revelations of the 20th century. It overturned thousands of years of assumptions about the cosmos and led us into conceptual territory where our everyday intuitions fail us completely. For most of human history, people assumed the universe was static. It existed, unchanging, eternal. The stars moved in their fixed patterns across the sky, but the overall structure of the cosmos was permanent. This seemed obvious. If the universe were changing in some dramatic way, surely we would notice. The night sky looked the same year after year, century after century. The ancients saw the same constellations we see today. Even Einstein, when he developed his general theory of relativity in 1915, assumed the universe was static. His equations actually predicted an expanding or contracting universe, but Einstein found this so disturbing that he added a term called the cosmological constant to force the equations to describe a static cosmos. The idea of a changing universe seemed absurd. He later called this addition the biggest blunder of his career. The observational evidence for an expanding universe came in the 1920s, primarily from the work of Edwin Hubble. Hubble was studying distant galaxies using the 100-inch telescope at Mount Wilson Observatory in California, then the largest telescope in the world. He was trying to measure how far away these galaxies were, and whether they were moving toward us or away from us. To measure motion toward or away, astronomers use something called redshift. When an object moves away from you, the light it emits gets stretched to longer wavelengths. Longer wavelengths appear redder, so this stretching is called redshift. When an object moves toward you, the light gets compressed to shorter, bluer wavelengths, called blue shift. By measuring the redshift of galaxies, Hubble could determine whether they were moving away from us or toward us. What Hubble found was remarkable. Almost every galaxy he observed was redshifted. They were all moving away from us, and more importantly, the farther away a galaxy was, the faster it was moving away. This relationship, now called Hubble's law, was the first direct evidence that the universe is expanding. At first, you might think this means Earth is at the center of some cosmic explosion, with everything flying away from us. But that's not what's happening. The expansion of the universe isn't like an explosion at all. It's something far stranger. When we say the universe is expanding, we don't mean that galaxies are flying through space away from some central point. We mean that space itself is stretching. The fabric of space-time is expanding, carrying galaxies along with it. It's not that galaxies are moving through space, it's that there's more space between galaxies over time. Here's an analogy that might help. Imagine you have a balloon, and you draw dots on its surface with a marker. Each dot represents a galaxy. Now imagine inflating the balloon. As the balloon expands, the dots move apart from each other. But the dots aren't moving across the surface of the balloon. The surface itself is stretching, carrying the dots with it. Every dot sees every other dot moving away. No dot is at the center, because there is no center. The expansion is happening everywhere. The universe is like the surface of that balloon, except three-dimensional instead of two-dimensional. Space itself is stretching, and galaxies are carried along by that stretching. From our perspective on Earth, it looks like all galaxies are moving away from us, but an observer in any other galaxy would see the same thing. From their perspective, all galaxies will be moving away from them. No galaxy is at the center of the expansion because there is no center. The expansion is happening everywhere, at every point in space. This expansion has been going on since the Big Bang, about 13.8 billion years ago. In the early universe, everything was much closer together. As the universe expanded, the average distance between galaxies increased. Today, the expansion continues. Galaxies that were relatively close billions of years ago are now much farther apart. The expansion rate is described by a number called the Hubble constant, named after Edwin Hubble. This number tells you how fast space is expanding at a given distance. The current best estimate is about 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. So for every 3.26 million light years of distance, space is expanding at about 70 kilometers per second. This might not sound like much. 70 kilometers per second is fast by everyday standards, about 252,000 kilometers per hour. But remember, this expansion rate applies to every megaparsec of distance. If a galaxy is 2 megaparsecs away, the expansion rate is 140 kilometers per second. If it's 10 megaparsecs away, the expansion rate is 700 kilometers per second. The farther away something is, the more space there is between us and it, and the faster that space is expanding. The expansion of space doesn't affect everything equally. On small scales, other forces dominate. The atoms in your body are bound together by electromagnetic forces, far stronger than cosmic expansion. The Earth is held together by gravity. The solar system is bound by the sun's gravitational pull. Even our galaxy, the Milky Way, is held together by gravity strongly enough to resist the expansion. You don't need to worry about your body slowly stretching due to cosmic expansion. You don't need to worry about Earth drifting away from the sun. The expansion rate is incredibly weak compared to the forces that hold matter together. On the scale of a human body, the expansion amounts to less than the width of an atom over the course of a human lifetime. It's utterly negligible. But on the larger scales, where galaxies are separated by millions of light years of mostly empty space, gravity is too weak to hold things together. In these vast intergalactic voids, there's nothing to resist the expansion. Space stretches freely, carrying galaxies apart. This creates an interesting distinction that astronomers must constantly keep in mind. Galaxies have two kinds of motion. There's the recession velocity, which is the apparent motion away from us due to the expansion of space. And there's the peculiar velocity, which is actual motion through space caused by gravitational attraction to nearby mass. The Andromeda Galaxy illustrates this perfectly. Based on the expansion of space alone, Andromeda should be moving away from us like almost every other galaxy. But it's not. Andromeda is actually approaching the Milky Way at about 110 kilometers per second. Why? Because Andromeda and the Milky Way are close enough, and massive enough, that their mutual gravitational attraction overpowers the expansion of space between them. The two galaxies are falling toward each other despite the overall expansion of the universe. In about 4.5 billion years, these two galaxies will collide and merge. The collision will be spectacular on cosmic timescales, lasting hundreds of millions of years. Stars will be flung into new orbits. Gas clouds will compress and trigger bursts of star formation. The familiar spiral shapes of both galaxies will be destroyed, replaced eventually by a giant elliptical galaxy that astronomers have nicknamed Milkomeda. This gravitational attraction isn't unique to Andromeda and the Milky Way. Throughout the universe, gravity creates local motions that overlay the overall expansion. The Milky Way, along with Andromeda and dozens of smaller galaxies, belongs to a structure called the local group. All these galaxies are gravitationally bound to each other, orbiting their common center of mass, moving through space in complex patterns. But even the local group isn't stationary. It's being pulled through space by the gravity of larger structures. The local group is falling toward the Virgo cluster at several hundred kilometers per second. And the Virgo cluster itself is being pulled toward an even larger concentration of mass, called the Great Attractor. The Great Attractor is a gravitational anomaly located about 250 million light-years away in the direction of the constellation Centaurus. It's not a single object, but a region of space containing several massive galaxy clusters. The combined gravity of all this mass is pulling the Milky Way, the local group, the Virgo cluster, and thousands of other galaxies toward it at about 600 kilometers per second. For decades, the Great Attractor was mysterious because it lies behind the plane of the Milky Way, where dust and stars block our view. We could detect its gravitational influence, but we couldn't see what was causing it. Only with infrared telescopes that could peer through the obscuring dust did astronomers finally map the galaxy clusters responsible. Beyond the Great Attractor lies an even more massive structure called the Shapley supercluster. This enormous concentration of galaxies appears to be the dominant gravitational influence in our region of the universe, pulling everything toward it. The Shapley supercluster contains more than 8,000 galaxies, and is one of the densest known concentrations of matter in the observable universe. These bulk flows, these rivers of galaxies streaming through space under the influence of gravity, complicate our measurements of the expansion. When we measure a galaxy's redshift, we're seeing the combination of the cosmic expansion and any peculiar velocity the galaxy might have. Separating these two effects requires careful analysis and large statistical samples. For nearby galaxies, peculiar velocities can be significant compared to the expansion. A galaxy only 10 megaparsecs away has a recession velocity of about 700 kilometers per second due to expansion. But if it also has a peculiar velocity of 300 kilometers per second toward us, we'd measure a net recession of only 400 kilometers per second. The peculiar velocity masks part of the expansion. For distant galaxies, peculiar velocities become negligible compared to the expansion. A galaxy 1,000 megaparsecs away has a recession velocity of 70,000 kilometers per second. A peculiar velocity of a few hundred kilometers per second barely affects this number. The expansion dominates completely. At a certain distance, the cumulative expansion becomes faster than the speed of light. Beyond that distance, space is expanding so fast that light emitted toward us can never actually reach us. The expansion carries the light away faster than it can make progress toward us. This critical distance is called the Hubble radius or the Hubble sphere. With the current expansion rate, the Hubble radius is about 14.4 billion light years. Anything beyond this distance is receding from us faster than light due to the expansion of space. This doesn't violate Einstein's prohibition on faster than light travel because nothing is moving through space faster than light. The galaxies themselves might be nearly stationary in their local region of space, but the space between us and them is expanding so rapidly that the cumulative effect is a recession faster than light. Speed. Now, you might think that anything beyond the Hubble radius is forever invisible to us, but this isn't quite right. The Hubble radius changes over time as the expansion rate changes. Light that was initially being carried away by expansion can eventually start making progress toward us if the expansion slows down. This brings us to one of the most shocking discoveries in the history of science. In the 1990s, two independent teams of astronomers set out to measure how fast the expansion of the universe was slowing down. Everyone expected the expansion to be decelerating. The gravitational attraction of all the matter in the universe should act like a brake, gradually slowing the expansion over time. The only question was how quickly. To measure this deceleration, astronomers needed a way to determine distances to very remote galaxies with high precision. They needed what astronomers call standard candles, objects whose true brightness is known, so that by measuring how bright they appear, you can calculate how far away they are. The perfect standard candle turned out to be a particular type of exploding star, called a Type 1a supernova. These supernovae occur in binary star systems, when a white dwarf star accumulates matter from a companion star until it reaches a critical mass of about 1.4 solar masses. At that point, the white dwarf can no longer support itself against gravity and undergoes a runaway nuclear fusion reaction, destroying itself in a colossal explosion. Because all Type 1a supernovae explode at essentially the same mass, they all release essentially the same amount of energy. They all have roughly the same peak brightness, about 5 billion times the luminosity of the Sun. This makes them excellent standard candles. If you see a Type 1a supernova and measure how bright it appears, you can calculate how far away it is by comparing its apparent brightness to its known true brightness. A supernova that appears 4 times fainter is twice as far away. 2 teams took up the challenge. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt at Mount Stromlo Observatory in Australia, with Adam Rees playing a key role in the analysis. Both teams were searching for distant Type 1a supernovae to measure the expansion history of the universe. Finding these supernovae was painstaking work. Type 1a supernovae are rare, occurring perhaps once per century in a typical galaxy. To find enough of them, astronomers had to monitor thousands of galaxies, comparing images taken weeks apart, looking for the sudden appearance of a new point of light. When they found a candidate, they had to quickly obtain a spectrum to confirm it was indeed a Type 1a supernova, and not some other type of stellar explosion. The work required international collaboration, with telescopes around the world contributing observations. What they found was completely unexpected. Both teams discovered that distant supernovae were fainter than they should be. This meant the supernovae were farther away than expected. And this meant the universe's expansion wasn't slowing down at all. It was speeding up. The expansion of the universe is accelerating. This result was so shocking that both teams checked and rechecked their data obsessively. They looked for errors in their observations, their analysis, their assumptions about Type 1 supernovae. They considered whether dust between us and the supernovae might be dimming the light. They examined whether distant supernovae might be intrinsically different from nearby ones. They found none of these explanations satisfactory. The data was clear. Distant supernovae were about 25% fainter than expected for a decelerating universe. The universe was expanding faster now than it was in the past. The two teams published their results in 1998 and 1999. The scientific community was stunned. This was not a minor revision of existing theory. This was a complete overturning of expectations. Something was pushing the universe apart, counteracting gravity, making the expansion accelerate. That something is called dark energy. We don't know what dark energy is. It's one of the biggest mysteries in modern physics. But we know it exists because we can measure its effects. Dark energy makes up about 68% of the total energy content of the universe. It pervades all of space, and its effect is to push space apart, making the expansion accelerate. What could dark energy be? Physicists have proposed various explanations. It might be the energy of empty space itself, a kind of vacuum energy that exerts negative pressure and causes expansion. This idea connects to Einstein's cosmological constant, the term he added to his equations and later regretted. Perhaps Einstein was right after all, just for the wrong reasons. Alternatively, dark energy might be a new kind of field that pervades the universe, sometimes called quintessence. Unlike the cosmological constant, which would be truly constant, quintessence could change over time, potentially explaining why the universe wasn't always accelerating. Or dark energy might be a sign that our theory of gravity is incomplete on the largest scales. Perhaps general relativity needs modification when applied to the entire universe. Perhaps what we interpret as dark energy is really a symptom of our misunderstanding of gravity itself. The discovery was so important that Perlmutter, Schmidt, and Ries were awarded the Nobel Prize in Physics in 2011. The prize citation noted that they had discovered the accelerating expansion of the universe through observations of distant supernovae. The discovery of dark energy changed everything about how we understand the long-term fate of the universe, and it has profound implications for the concept of distance. If the expansion was slowing down, Eventually, light from anywhere in the universe could reach us, given enough time. The Hubble radius would keep growing, eventually encompassing everything. We could, in principle, eventually see the entire universe. But because the expansion is accelerating, the opposite is happening. The expansion is carrying galaxies away faster than our ability to observe them can grow. There are galaxies we can see right now whose light will never reach us again. Light they emit today will never arrive at Earth, no matter how long we wait. This creates a boundary called the cosmic event horizon. It represents the maximum distance from which light emitted today will ever reach us. The cosmic event horizon is currently about 16 to 17 billion light years away. Any light emitted from beyond this distance today will never reach Earth. The expansion will carry it away forever. This is a profound change from what astronomers believed for most of the 20th century. Before the discovery of accelerating expansion, the assumption was that the observable universe would grow forever. Patient observers could eventually see everything. Now we know this isn't true. The observable universe has a maximum extent. Beyond the cosmic event horizon lies a realm we will never see, never communicate with, never know anything about. Even more troublingly, the cosmic event horizon is moving inward relative to the galaxies. As the expansion accelerates, more and more galaxies are being carried beyond this horizon. Galaxies that we can see today, galaxies whose light has already reached us, will eventually vanish over the cosmic horizon. We'll see their light grow redder and fainter as they accelerate away, until finally they disappear entirely. Interestingly, while we know dark energy exists and drives this accelerating expansion, measuring exactly how fast the expansion is occurring has become increasingly controversial. This is called the Hubble tension, and it's one of the most significant puzzles in modern cosmology. The Hubble constant, which describes the current expansion rate, can be measured in two fundamentally different ways. The first method uses observations of the local universe. Astronomers measure the distances and recession velocities of nearby galaxies using Cepheid variable stars and Type 1a supernovae as distance indicators. This method gives a Hubble constant of about 73 kilometers per second per megaparsec. The second method uses observations of the cosmic microwave background, the ancient light from the early universe. By analyzing the tiny variations in this radiation, cosmologists can determine the conditions of the early universe and calculate what the Hubble constant should be today based on our theoretical models. This method gives a Hubble constant of about 67 kilometers per second per megaparsec. These two numbers should agree. They don't. The discrepancy is about 9%, which might not sound like much, but both measurements have become so precise that this difference is highly statistically significant. It's not a matter of measurement error. Something is wrong with either our observations, our models, or both. This tension has persisted for years despite increasingly precise measurements. Each new dataset confirms the discrepancy rather than resolving it. Local measurements consistently give higher values. Cosmic microwave background measurements consistently give lower values. The universe seems to be expanding at two different rates, depending on how you look at it. Some physicists believe the Hubble tension points to new physics beyond our current understanding. Perhaps dark energy changes. over time in ways our models don't capture. Perhaps there was an additional burst of expansion in the early universe that we haven't accounted for. Perhaps there's some unknown particle or force that affects the expansion differently at different epochs. Others believe the tension will eventually be resolved by identifying some systematic error in one or both measurement methods. Perhaps type 1. Supernovae aren't quite as standard as we thought. Perhaps our models of the early universe are missing something. The debate continues, and resolution remains elusive. Regardless of the exact value of the Hubble constant, the accelerating expansion creates a profound problem for the concept of distance. When we ask how far away a distant galaxy is, the answer depends critically on what we mean. The light from a distant galaxy has been traveling for a certain amount of time. We call this the look-back time. For a galaxy whose light has been traveling for 10 billion years, the look-back time is 10 billion years. We're seeing the galaxy as it was 10 billion years ago. But where was the galaxy when the light was emitted? Because the universe was smaller then, the galaxy was closer. And where is the galaxy now? The universe has been expanding the entire time the light was traveling. The galaxy has been carried farther and farther away by the expansion of space. For very distant galaxies, these different distances can differ by factors of 2 or 3 or more. The light travel distance, the emission distance, and the current distance are all different. There's no single right answer to how far away the galaxy is. Consider a galaxy whose light has been traveling for 10 billion years. When that light was emitted, the galaxy was roughly 5 billion light years away by proper distance. But today, after 10 billion years of expansion, that galaxy is about 18 billion light years away. Is the galaxy 10 billion light years away? 5 billion? 18 billion? All of these answers are correct for different definitions of distance. This isn't just a matter of semantics. It reflects something deep about the nature of space-time. Distance, as a single well-defined quantity, breaks down when applied to an expanding universe. Different definitions of distance capture different physical aspects of the separation between objects, but none of them corresponds to our intuitive everyday notion of how far apart things are. Astronomers have responded to this ambiguity by largely abandoning distance as a primary way of describing cosmic objects. Instead, they use redshift. The redshift tells you directly how much the universe has expanded since the light was emitted. A redshift of 1 means the universe has doubled in size. A redshift of 2 means it has tripled. The cosmic microwave background has a redshift of about 1,100, meaning the universe has expanded by a factor of about 1,100 since that light was emitted. Redshift is directly measurable and unambiguous. You observe the spectrum of a distant object, identify spectral lines from known elements, and measure how much those lines have shifted toward longer wavelengths. No assumptions about cosmological models are needed. The redshift is what it is. From redshift, you can calculate various distances if you want, but this requires assuming a cosmological model with specific values for the Hubble constant, the density of matter, the density of dark energy, and so forth. Different assumptions give different distances. The redshift remains the same. This shift from distance to redshift represents a fundamental change in how we conceptualize the universe. We've moved from a spatial picture where objects are located at various distances in a fixed space, to a temporal picture, where objects are located at various points in cosmic history. When an astronomer says a galaxy is at redshift 5, they're not primarily telling you where it is in space. They're telling you when it is in cosmic history. You're seeing that galaxy as it was when the universe was about 1 billion years old, less than 8% of its current age. The spatial location is secondary, derivative, and depends on which definition of distance you choose. The expansion of space has transformed distance from a simple, intuitive concept into something far more complicated. Space isn't a static stage on which cosmic events play out. Space itself is a dynamic participant, stretching and growing, carrying objects along with it, making the very notion of separation ambiguous. And we haven't even reached the strangest part yet. The cosmic horizons, the boundaries beyond which information cannot pass, create regions of space where distance isn't just complicated, it becomes essentially meaningless. Where objects exist that we can see but can never reach, and objects exist that we will never see at all. These horizons mark the true edges of our knowable universe. Beyond them lies territory where the concept of distance finally breaks down completely. We now need to confront the boundaries of the observable universe directly. These aren't physical walls or barriers. They're horizons, limits on what we can see and interact with, arising from the finite speed of light and the expansion of space. There are several different cosmic horizons, each marking a different kind of boundary. Understanding them is crucial for understanding why distance ultimately stops meaning anything at cosmic scales. The first and most fundamental is the particle horizon. This is the maximum distance from which light has had time to reach us since the Big Bang. Because the universe has been expanding the whole time, the particle horizon is much farther than you might naively expect. Objects that emitted light early in the universe's history were much closer then, but have since been carried far away by expansion. The current particle horizon is about 46.5 billion light-years in every direction. This defines the observable universe, a sphere roughly 93 billion light-years in diameter, with Earth at the center. Everything within this sphere has had time to send light to us since the Big Bang. Everything outside this sphere has not. Life from beyond the particle horizon hasn't had time to reach us yet. Note that this doesn't mean nothing exists beyond the particle horizon. It almost certainly does. The universe is probably much larger than the observable part, possibly infinite. But we can't see beyond the particle horizon. We have no information about what's out there. For all practical purposes, the particle horizon is the edge of our knowable universe. The particle horizon isn't a fixed boundary. It's constantly expanding outward at the speed of light, as more and more light has time to reach us. Every second, light from slightly more distant regions arrives on Earth for the first time. The particle horizon grows by 1 light second every second. In principle, we're constantly gaining access to more of the universe. But here's where the accelerating expansion creates a cruel twist. While the particle horizon keeps expanding outward, the cosmic event horizon is shrinking relative to the galaxies. That boundary beyond which no new light can ever reach us is creeping closer. This creates a strange situation. We can see galaxies that are already beyond the event horizon. Light they emitted billions of years ago has reached us and continues to arrive. But light they emit today right now, will never reach Earth. We're seeing their past, but we'll never see the future. These two horizons, the particle horizon and the event horizon, define the edges of our observable universe in different ways. The particle horizon tells us what we can see from the past. The event horizon tells us what we'll ever be able to see from the present and future. But there's a third boundary that's even more restrictive, one that astronomers rarely discuss, but that fundamentally limits our connection to the cosmos. This is the boundary of the affectable universe. The observable universe contains everything we can see. But can we interact with everything we can see? Can we send signals to every galaxy whose light reaches our telescopes? Can we, even in principle, ever influence events in those distant places? The answer is no. The affectable universe is much smaller than the observable universe. Think about it this way. To affect something, to send it a signal or eventually travel there, we need to send something toward it. The fastest we can send anything is the speed of light. But while our signal travels outward, the expansion of space is carrying distant galaxies away from us. For nearby galaxies, our signal can catch up. For distant galaxies, the expansion carries them away faster than our signal can approach. The boundary of the affectable universe is the maximum distance at which a signal we send today could ever arrive. Beyond this boundary, even a message traveling at the speed of light, sent right now, would never reach its destination. The expansion would carry the target away faster than the message could approach. This boundary is roughly the same as the cosmic event horizon, about 16 to 17 billion light years. Any galaxy beyond this distance is not only unable to send us new information, but we're equally unable to send information to it. We are causally disconnected. Nothing we do can ever affect them, and nothing they do can ever affect us. This means the observable universe is much larger than the affectable universe. We can see galaxies that we can never reach, never signal, never influence in any way. We're like ghosts watching a scene we cannot touch. The light from those galaxies reaches us, carrying information about their past, but we cannot respond. We cannot participate. We can only observe. Consider a galaxy we observe at a distance of 30 billion light years. We see it as it was billions of years ago. We might observe its stars, study its structure, analyze its composition, but we can never send a message that would arrive there. We can never visit. Even if a civilization exists in that galaxy and they're observing us right now, seeing Earth as it was billions of years ago, neither of us can ever make contact. The expansion has separated us forever. This distinction between observable and affectable matters profoundly for questions about extraterrestrial life. When we ask whether we're alone in the universe, we usually mean the observable universe. But perhaps the more meaningful question is whether we're alone in the affectable universe. Even if intelligent life teems throughout the cosmos, if most of it lies beyond the affectable boundary, we will never know. We will never make contact. For all practical purposes, we might as well be alone. The various cosmic horizons create a layered structure of accessibility around us. At the innermost layer, things are close enough that light travel times are short. We can observe events nearly as they happen. We can potentially visit these locations and affect what happens there. This includes the solar system and the nearest stars. At greater distances, light travel times become significant. We see events years or centuries or millions of years after they occurred. We can still observe, and we can still send signals that will eventually arrive. But by the time we act on what we see, the situation will have changed dramatically. This includes most of the Milky Way and nearby galaxies. At still greater distances, approaching the event horizon, we can observe events that occurred billions of years ago, but our ability to affect those regions is marginal at best. Signals we send might barely arrive before the expansion carries those regions beyond reach forever. Beyond the event horizon, we have observational access only to the past. We can see what those regions look like billions of years ago, but we'll never see their present or future, and we can never affect them in any way. Beyond the particle horizon, we have no access at all. We can only speculate about what exists there based on theory and extrapolation. This layered structure fundamentally challenges our understanding of distance. Distance, as we normally think of it, implies potential accessibility. If something is a certain distance away, you could, in principle, go there. You could observe it, interact with it, affect it. But cosmic distance doesn't work like that. Beyond certain horizons, there is no accessibility. The distance is not a measure of how far you'd have to travel, but a measure of how separated you are from any possibility of interaction. Now, let's talk about what it's like to approach these horizons. What happens to observations as you get closer to the edges? As we observe objects at higher and higher redshift, approaching the particle horizon, something curious happens. The objects don't just get fainter, they also appear to freeze in time. This is due to time dilation from the expansion. When we look at a distant galaxy, we're seeing light that has been stretched by the expansion. But it's not just the wavelength that's stretched. Time intervals are also dilated. Events that took 1 second at the galaxy appear to take longer when we observe them, stretched by the same factor as the wavelength. For a galaxy at redshift 10, time appears to pass about 11 times more slowly than here. A supernova that lasts 2 weeks in the galaxy's reference frame appears to last about 5 months in ours. The galaxy seems to be in slow motion. As we approach the particle horizon, the redshift increases without limit. Objects at the very edge of the observable universe would be infinitely redshifted. Their light would be stretched to infinite wavelength, carrying zero energy. Time would appear to stop completely. We would see them frozen, never changing, caught in an eternal instant. In practice, we can't actually observe objects at infinite redshift. The light is too faint, stretched beyond detection. The cosmic microwave background, at redshift about 1100, is the oldest light we can see. It comes from a time when the universe first became transparent, about 380,000 years after the Big Bang. Before that, the universe was opaque, and no light from earlier times survives. But theoretically, if we could somehow observe objects at even higher redshift, approaching the particle horizon, they would appear increasingly frozen in time. The ultimate edge of the observable universe is a surface where time stands still, where nothing ever changes, where light arrives with zero energy. This is deeply strange. Distance at the particle horizon has become entangled with time in a way that makes them inseparable. The edge isn't really a place in space. It's a limit on time, on the past we can access. Beyond it lies more space, presumably, but no information about it can ever reach us. The cosmic horizons create other strange effects on our observations. One of the most remarkable is gravitational lensing, where mass concentrations between us and distant objects bend light in ways that distort, magnify, and multiply images. Einstein's general relativity predicts that mass curves space-time, and light follows these curves. When light from a distant galaxy passes near an intervening mass, such as another galaxy or a galaxy cluster, its path is bent. This gravitational lensing can act like a cosmic magnifying glass, brightening and enlarging images of distant objects. In extreme cases, lensing creates multiple images of the same object. The light takes different paths around the intervening mass, and each path creates a separate image. The most famous example is the Einstein cross, where a distant quasar appears as 4 separate images arranged in a cross pattern around a foreground galaxy. All 4 images show the same quasar, but each image represents light that took a different path through curved space-time. Even more remarkably, each image shows the quasar at a slightly different time. The different paths have different lengths, so light traveling along each path takes a different amount of time to reach us. When astronomers observe variations in the quasar's brightness, they see those variations appear in each image at different times, offset by days or weeks, depending on the path length differences. This raises profound questions about distance and position. If a quasar appears in 4 different places in the sky, where is it really? What is its true distance? The light travel time is different for each image. The apparent position is different for each image. The concept of a single, well-defined location breaks down completely. The Hubble Space Telescope has captured stunning images of gravitational lensing in galaxy clusters. The Hubble Frontier Fields program specifically targeted massive galaxy clusters to use them as cosmic telescopes. The cluster's enormous gravity bends and magnifies light from far more distant galaxies behind them, allowing astronomers to see galaxies that would otherwise be too faint to detect. In these images, distant galaxies appear as arcs and streaks, their shapes distorted by the uneven magnification of the gravitational lens. Some galaxies appear multiple times as separate images. The same galaxy might appear on opposite sides of the cluster, each image showing it at a different moment in its history. These lensed images have allowed astronomers to study galaxies from the early universe in unprecedented detail. Galaxies at redshifts of 9 or 10, seen as they were less than 500 million years after the Big Bang, have been magnified by factors of 10 or 20 or even more. Without the cosmic magnifying glass, these galaxies would be invisible specks. With it, we can study their structure and composition, but the lensing also undermines any simple notion of distance. A galaxy might be 30 billion light-years away in proper distance, but appear magnified as if it were much closer. Its light has been bent, delayed, and distorted by intervening mass. The image we see doesn't correspond to any straightforward line of sight. The galaxy's apparent position in the sky isn't its true direction. Everything about the observation has been warped by the curved geometry of space-time. In some cases, lensing can create complete rings of light called Einstein rings. If a distant source is perfectly aligned behind a massive lens, the light is bent equally in all directions, creating a ring of light centered on the lens. These rings are among the most beautiful and strange objects in astronomy, perfect circles of light from galaxies billions of light years away, their images smeared into halos by curved space-time. The existence of gravitational lensing demonstrates that light doesn't travel in straight lines through the universe. It follows the curves of space-time, bending around masses, taking paths that depend on the distribution of matter along the way. This means that every observation we make is potentially affected by lensing to some degree. The universe we see is not a straightforward projection of what's out there. It's a distorted view, warped by every mass concentration between us and what we're observing. For nearby objects, the distortion is negligible. But for the most distant objects, near the edge of the observable universe, the accumulated lensing from billions of light years of intervening structure can significantly affect what we see. The cosmic web of galaxies and dark matter creates subtle lensing effects throughout the universe, slightly distorting the images of everything behind it. Astronomers have learned to use this weak lensing to map the distribution of matter in the universe, including dark matter that can't be seen directly. By measuring the tiny distortions in the shapes of millions of distant galaxies, they can infer where mass is concentrated in the foreground. It's like inferring the shape of a bathroom window by looking at how it distorts the view of trees outside. But this technique relies on statistical analysis of many galaxies. For any individual galaxy, we can't know exactly how much its image has been distorted. We see an image, but we can't be certain that image accurately represents the galaxy's true shape, position, or brightness. The curved geometry of space-time introduces uncertainty into every observation. Now let me describe something that will happen gradually over cosmic time. Something that illustrates the slow erasure of the universe from our view. This is the story of the last photon. Right now, we can see about 2 trillion galaxies in the observable universe. Each of these galaxies contains billions or hundreds of billions of stars. The universe appears full, rich with structure, teeming with matter and light. But this will change. The accelerating expansion is pushing galaxies away from us faster and faster. One by one, they will cross the cosmic event horizon and begin to disappear from our observable universe. The most distant galaxies will go first. Galaxies near the current edge of the observable universe are already receding at enormous speeds. Their light is already highly redshifted, arriving weakly after billions of years of travel. As the expansion accelerates, these galaxies will dim further, their light stretching to longer and longer wavelengths. Imagine watching a single distant galaxy as it approaches and crosses the cosmic event horizon. At first, the galaxy is bright enough to observe clearly. We can see its spiral arms, its star-forming regions, its central bulge. Spectra reveal its composition and the motions of its stars. As the expansion accelerates, the galaxy begins to redden. Blue light from young, hot stars stretches into green, then yellow, then red. The galaxy appears to age before our eyes, not because it's actually aging faster, but because we're seeing it progressively redshifted. Eventually, all visible light from the galaxy shifts into the infrared. To our eyes, the galaxy would disappear, though infrared telescopes could still detect it. the redshifting continues. Infrared stretches into microwaves, then into radio waves. Each photon that reaches us carries less and less energy. The galaxy grows fainter and fainter. Not because it's actually dimming, but because its light is being stretched into oblivion. Time dilation compounds the effect. As the galaxy approaches the event horizon, time appears to slow down for it from our perspective. Processes that take a year in the galaxy's frame appear to take decades, then centuries, then millennia in ours. The galaxy seems to freeze, its evolution grinding to a halt. There will be a last photon from that galaxy. One final quantum of light will leave the galaxy, travel for billions of years, and arrive at Earth. After that, nothing. The galaxy will have crossed the event horizon. Every subsequent photon it emits will be carried away by expansion, never to reach us. We will never know when that last photon arrives. It will look like every other photon from that galaxy, incredibly redshifted and faint, carrying an infinitesimal amount of energy. Some detectors somewhere might register it, but we'll have no way of knowing it was the last. We'll simply notice, gradually, that no more photons are coming. The galaxy will have vanished. This fate awaits every galaxy beyond the local group. The Virgo cluster, about 54 million light-years away, will eventually send us its last photon. The Coma cluster will follow. Every galaxy cluster, every supercluster, every filament of the cosmic web that isn't gravitationally bound to us will eventually vanish. The timeline for this erasure is long by human standards, but short by cosmic standards. In about 100 billion years, virtually every galaxy beyond our local group will have crossed the event horizon. The sky will be empty. Future astronomers, if any exist in that distant era, will see a universe very different from the one we see. They'll observe their own galaxy, the merged remnant of the Milky Way and Andromeda that astronomers have nicknamed Milkomeda. They'll see the other small galaxies of the former local group, still gravitationally bound, orbiting within a shared dark matter halo. But when they look out into the depths of space, they'll see nothing. No other galaxies, no clusters, no cosmic web, just darkness extending forever in every direction. The cosmic microwave background will still exist, technically, but by then it will be stretched beyond any possible detection. Its wavelength will be billions of times longer than it is today. Its temperature will be a tiny fraction of a degree above absolute zero. No telescope could ever detect it. These future observers will have no evidence that the universe was ever any different. They won't see the expansion because there will be no distant galaxies to observe receding. They won't see the cosmic microwave background because it will be too faint. They might deduce from theory that the universe should be larger than what they observe, but they'll have no way to confirm it. They might develop physics and astronomy to a high level. They might understand stellar evolution, planetary formation, the nature of gravity and light. But their cosmology will be fundamentally limited. They'll think they live in a small, static universe consisting of a single galaxy surrounded by infinite empty space, and they'll be wrong. The universe will still be out there, full of trillions of galaxies, but those galaxies will be beyond the event horizon, causally disconnected, forever unobservable. For these future astronomers, those galaxies might as well not exist. This raises a profound question about our own situation. We think we understand the universe. We've mapped billions of galaxies. We've detected the cosmic microwave background. We've measured the expansion and discovered its acceleration. We've constructed detailed models of cosmic history going back to a fraction of a second after the Big Bang. But is our view complete? Are there aspects of the universe that were visible in the past, but have since disappeared over the horizon? Are there phenomena we can never detect because the evidence has been stretched beyond detection or carried beyond our reach? As far as we know, we live in a privileged era. The universe is old enough for complex structures to have formed, but young enough that we can still see the evidence of its history. The cosmic microwave background is still detectable, distant galaxies are still visible, the expansion is measurable. We have access to information that future observers won't have. But we can't be entirely certain that we're not missing something. The universe might have properties or structures that were only visible during a brief window of cosmic time, now closed. We might be in the position of those future astronomers, thinking we understand the cosmos while missing something fundamental that's already disappeared from view. This uncertainty is built into the nature of cosmic horizons. They don't just limit what we can see, they limit what we can know. And that limitation applies not just to the future, but potentially to the past as well. The concept of cosmic horizons transforms our understanding of the universe from a vast but unified space into a collection of causally disconnected regions. Within our observable universe, we can in principle observe everything. Within our affectable universe, we can potentially interact with everything. But these regions don't encompass all of reality. They're just our accessible portion of something much larger. Beyond the horizons lies more universe, presumably obeying the same physical laws, containing galaxies and stars similar to the ones we can see, but we'll never have direct evidence. We'll never see those regions. We can only believe they exist based on theoretical reasoning and the assumption that the universe doesn't end just because our ability to observe it does. What does distance mean when applied to regions beyond the horizon? In one sense, you can extrapolate numbers. If the universe is roughly uniform, you can estimate that there should be a certain number of galaxies per cubic megaparsec, and you can calculate how many galaxies should exist beyond the horizon based on that density. But these numbers are purely theoretical. They don't correspond to anything observable. You can't point to a galaxy beyond the horizon because you can't see it. You can't measure its redshift because no light from it has reached you. Any distance you assign is a mathematical extrapolation, not an observation. In another sense, distance beyond the horizon is infinite in the only way that matters. You can never go there. You can never communicate with anything there. No matter how long you wait or how fast you travel, those regions are forever beyond reach. They are effectively infinitely far away, regardless of what number a theoretical calculation might produce. We've now mapped the edges of our accessible universe. The particle horizon defines what we can see from the past. The event horizon defines what we'll ever be able to see. The boundary of the affectable universe defines what we can ever influence. These horizons carve up space-time into regions with fundamentally different relationships to us. Within all these horizons, distance still means something, though it's complicated by expansion, redshift, and curved geometry. At the horizons, distance becomes strained. different definitions diverging wildly. Beyond the horizons, distance becomes meaningless in any practical sense. The universe, it turns out, isn't a single continuous space where distance uniformly describes separation. It's a patchwork of regions with different accessibility, different observability, different causal connections to us. Distance works within each region, sort of, with caveats. But across the horizons, distance fails completely. This is the edge of everything. Not a wall in space, not a boundary you could touch or see, but a limit on knowledge itself. Beyond it lies more universe, presumably, but that universe is forever beyond our reach. The distance to it isn't really distance at all. It's a measure of eternal separation, of permanent unknowability, and this edge is slowly creeping inward. Every galaxy that crosses the event horizon is lost forever. Every photon that makes its final journey to Earth marks the end of our connection to its source. The observable universe is shrinking galaxy by galaxy, photon by photon, as the accelerating expansion carries the cosmos away. So what does all this mean for the concept of distance itself? How have astronomers responded to this breakdown? And what does it tell us about our place in a cosmos that extends far beyond what we can ever know? We've traveled a long way from the simple concept of distance we started with. We've seen how the finite speed of light means we only see the past, never the present. We've seen how the expansion of space complicates distance, making different definitions give different answers. We've seen how cosmic horizons create boundaries beyond which information cannot pass. Now we need to confront what all this means for the concept of distance itself. And the conclusion is profound. At the largest cosmic scales, distance as we normally understand it ceases to function as a meaningful concept. Let me be precise about what I mean by this. Distance in our everyday experience has certain properties. It's symmetric. If the distance from your house to the grocery store is 2 miles, then the distance from the grocery store to your house is also 2 miles. It satisfies the triangle inequality. The distance from point A to point C is less than or equal to the distance from A to B plus the distance from B to C. It's consistent over time. If I measure the distance between 2 buildings today and measure it again tomorrow, I get the same answer. These properties reflect our intuitive understanding of space as a container that things occupy. Space has a fixed structure, and distance measures separation within that structure. But cosmic distance doesn't have these properties. Cosmic distance isn't symmetric in a meaningful sense. The light travel distance from a galaxy to us is how long the light took to travel. But this isn't the same as the light travel distance from us to that galaxy. Because the universe has changed in the meantime, if we sent light to that galaxy now, it would take a different amount of time than the light from that galaxy took to reach us, because the expansion has proceeded. For galaxies beyond the event horizon, light we send will never arrive at all, making the distance from us to them effectively infinite, while the distance from them to us, in terms of light we've already received, is finite. The expansion of space means there is no fixed structure to measure within. Space itself is changing. Any distance you measure now will be different later. The very ruler you would use to measure is stretching along with space. The horizons create fundamental asymmetries. We can see some galaxies, but they cannot see events on Earth that happened after a certain time. Information flows one way across certain thresholds, not both. And most importantly, there's no privileged definition of distance. Multiple valid definitions give different answers for the same object. None of them is more correct than the others. They're all measuring something, but what they're measuring isn't a simple property of space. Before we explore the philosophical implications of this breakdown, let's examine how astronomers actually measure cosmic distances in practice. This will reveal just how precarious our knowledge of cosmic distances really is. Measuring distances in astronomy is extraordinarily difficult. We can't stretch a tape measure to a distant star. We can't bounce radar off a galaxy and time the echo. We have to use indirect methods, each building on the previous one, in what astronomers call the cosmic distance ladder. The first rung of the ladder is parallax. As Earth orbits the Sun, our perspective on nearby stars shifts slightly. A star observed in January when Earth is on one side of the Sun appears in a slightly different position than the same star observed in July, when Earth is on the opposite side. By measuring this shift, called the parallax angle, and knowing the diameter of Earth's orbit, simple trigonometry gives the distance to the star. Parallax is the most direct and reliable distance measurement in astronomy. It's basic geometry, the same principle that surveyors use on Earth. But it only works for relatively nearby stars. The more distant a star, the smaller its parallax angle, and eventually the angle becomes too small to measure accurately. For most of history, parallax could only measure distances to stars within a few hundred light years. But the Gaia Space Telescope, launched by the European Space Agency in 2013, has revolutionized parallax measurements. From its orbit far from Earth's atmosphere, Gaia has measured the parallax of nearly 2 billion stars with unprecedented precision. It has extended reliable parallax distances to tens of thousands of light years, mapping a significant portion of the Milky Way in 3 dimensions. But even Gaia can't measure parallax for stars in other galaxies. The distances are simply too great. For those, we need the second rung of the ladder, Cepheid variable stars. In 1912, a young astronomer named Henrietta Swan Leavitt made a discovery that would change our understanding of the universe. Working at Harvard College Observatory, Leavitt was studying variable stars in the Small Magellanic Cloud, a small galaxy visible from the southern hemisphere. She noticed that certain pulsating stars, called Cepheids, showed a remarkable relationship between their brightness and the period of their pulsation. Brighter Cepheids pulsate more slowly. A Cepheid that pulses every 30 days is intrinsically brighter than one that pulses every 3 days. This period luminosity relationship means that by measuring how fast a Cepheid pulsates, you can determine its true brightness. And if you know how bright a star really is and how bright it appears, you can calculate how far away it is. Cepheid variables became the standard candles that allowed astronomers to measure distances to other galaxies for the first time. Edwin Hubble used Cepheids to prove that the Andromeda Nebula was actually a galaxy far outside the Milky Way, forever changing our conception of the universe's scale. Cepheids remain crucial distance indicators today, calibrating measurements out to about 100 million light years. But even Cepheids become too faint to observe in very distant galaxies. For those, we need an even brighter standard candle. Type 1, A supernovae. These exploding white dwarf stars all detonate at the same critical mass, releasing the same amount of energy, making them visible billions of light years away. By comparing their apparent brightness to their known true brightness, astronomers can calculate distances to the most remote galaxies. Here's the crucial point. Each rung of the cosmic distance ladder depends on the rungs below it. Type 1. A supernova distances are calibrated using Cepheid variables in nearby galaxies. Cepheid distances are calibrated using parallax measurements of Cepheids in our own galaxy. If any rung has systematic errors, those errors propagate upward, affecting all the rungs above. This is one reason the Hubble tension persists. The local measurement of the Hubble constant uses Cepheids and Type 1a supernovae, climbing the distance ladder rung by rung. If there are unknown systematic errors in the Cepheid calibration, or if Type 1 as supernovae aren't quite as standard as we thought, the resulting distances could be wrong, and the Hubble constant calculated from them would be wrong too. The cosmic distance ladder is an impressive achievement of human ingenuity. It's allowed us to map the universe on scales our ancestors couldn't have imagined. But it's also inherently uncertain. Each step introduces potential errors. The distances we measure to the most remote objects are not direct observations, but long chains of inference, each link depending on the ones before. When we say a galaxy is 10 billion light years away, we're not stating a directly measured fact. We're stating the result of a complex calculation involving parallax measurements of local stars, Cepheid observations in nearby galaxies, supernova measurements in distant galaxies, and assumptions about how all these objects behave. The number carries hidden uncertainties at every step. This doesn't mean cosmic distances are meaningless. The ladder has been tested extensively, and the different rungs generally agree with each other. But it does mean we should hold these numbers with appropriate humility. The universe is not obligated to make itself easy to measure. The geometry of the universe adds another layer of complexity to the breakdown of distance. In everyday life, we assume Euclidean geometry. Space is flat. Parallel lines stay parallel forever. The angles of a triangle add up to 180 degrees. The circumference of a circle is pi times its diameter. These relationships are so familiar that we barely think about them. But Einstein's general theory of relativity showed that mass and energy curve space-time. Near massive objects, geometry deviates from Euclidean. Space itself is warped. The familiar rules of geometry don't apply. On cosmic scales, the total mass and energy of the universe affects the overall geometry of space. If there's a certain critical amount of mass and energy, space is flat on average. If there's more than the critical amount, space is positively curved, like the surface of a sphere but in 3 dimensions. If there's less than the critical amount, space is negatively curved, like a saddle shape. Current measurements suggest that the universe is very close to flat, perhaps exactly flat, but we can't measure precisely enough to determine whether it's exactly flat or slightly curved one way or the other. And even if space is flat on average, there's a deeper question that flat or curved doesn't fully capture. What is the topology of the universe? Topology is different from geometry. Geometry tells you about curvature and angles and distances. Topology tells you about connectivity, about how space is connected to itself. Consider the surface of a cylinder. If you unroll it flat, It has the same geometry as a flat piece of paper. Parallel lines stay parallel. Triangles have angles that sum to 180 degrees. Locally, it's indistinguishable from flat space, but globally, it's different. If you walk far enough in one direction on a cylinder, you come back to where you started. The surface is finite even though it's flat. A torus, the shape of a donut surface, is similar. It's flat in the geometric sense, but it wraps around in two different directions. Walk far enough one way, you come back. Walk far enough the other way, you also come back. The surface is finite with no edges or boundaries. Could the universe have a similar topology? Could space be finite but unbounded, wrapping around on itself in one or more directions? This is a genuine scientific question, not just philosophical speculation. If the universe were a three-dimensional torus, space would wrap around in all three directions. You could, in principle, travel in a straight line and eventually return to your starting point. You wouldn't notice any boundary or edge. Space would simply connect back to itself. In such a universe, looking out into space would be like looking into a hall of mirrors. Light from distant galaxies could reach you by multiple paths, wrapping around the universe in different directions. You might see the same galaxy multiple times, in different directions, at different distances, showing different moments in its history. Astronomers have searched for evidence of cosmic topology in the cosmic microwave background. If the universe wraps around on a scale smaller than the observable universe, we might see repeating patterns in the microwave sky. Circles of matching temperature fluctuations could appear, revealing where our past light cone intersects itself after wrapping around. So far, no such patterns have been found. This doesn't prove the universe is infinite or simply connected. It only proves that if the universe wraps around, it does so on a scale at least as large as the observable universe. The topology could still be non-trivial. We just can't see far enough to detect it. But consider what a wrapped topology would mean for the concept of distance. In a torus universe, there will be multiple distances between any 2 points. You could travel directly from here to a distant galaxy, or you could go the long way, wrapping around the universe first. Both paths would be valid, but they'd have different lengths. Which one is the true distance? There's no clear answer. Distance would depend on which path you consider. The simple notion of the space between 2 points would become ambiguous in a fundamental way. Even more strangely, in a wrapped universe, the concept of direction would become ambiguous at large scales. Pointing toward a distant galaxy, you might be pointing along one path. But you could also point in the opposite direction and still be pointing toward the same galaxy, along a path that wraps around. The galaxy would be in multiple directions at once. We don't know if our universe has this kind of topology. Current evidence is consistent with a simply connected, possibly infinite universe, but the fact that we can't rule out wrapped topologies shows how much we don't know about the large-scale structure of space. And it reveals another way that distance can become problematic at cosmic scales. All of these factors combine to thoroughly undermine distance as a concept at cosmic scales. This doesn't mean we can't do astronomy. We can. We observe the cosmos, measure redshifts, map the distribution of galaxies, study the evolution of cosmic structure. We've built incredibly detailed models of the universe's history. But we do this using concepts other than distance. We use redshift, look-back time, co-moving coordinates. We describe the universe in terms that don't rely on the intuitive notion of how far away things are. Distance has become a secondary, derived quantity. You can calculate various distances from other observations if you want, but the distances aren't fundamental. They don't capture anything essential about the universe. They're just numbers we can compute, not properties that mean what distance means in everyday life. What does it mean to live in a universe where distance becomes so problematic? On one level, it means nothing for daily life. You still have to drive to work, and that distance is perfectly well defined. The grocery store is still 2 miles away. The breakdown of distance at cosmic scales doesn't affect how you navigate your neighborhood. But on another level, it changes how we understand our place in the universe. For most of human history, we thought of space as straightforward. It extended in all directions, uniformly, infinitely, or at least very far. Objects occupied positions in this space. Distance measured how far apart they were. Simple. Now we know the universe is stranger than that. Space expands. Distances change over time. Different ways of measuring give different answers. Horizons limit what we can see and what we can ever influence. The geometry might be curved. The topology might be wrapped. The intuitive framework of space as a container with well-defined distances fails at large scales. This is humbling. It reveals limits to our understanding. The concepts we evolved to navigate the African savanna, concepts that served us well for millions of years, fail when applied to the cosmos. We can't simply scale up our everyday intuitions. We have to develop new ways of thinking. Some philosophers have drawn striking conclusions from these observations. If regions beyond the cosmic event horizon can never be observed or affected, in what sense do they exist? This is a serious philosophical question. Some interpretations of physics hold that only observable things are real. By this standard, regions beyond the event horizon don't exist in any meaningful sense. Other philosophers disagree. They argue that existence doesn't depend on observability. The universe beyond the horizon presumably continues, obeying the same physical laws, containing galaxies and stars similar to the ones we can see. The fact that we can't observe it doesn't make it unreal. This debate echoes older philosophical arguments about the nature of reality. Is something real if no one can ever perceive it? Does existence depend on observation, or is it independent? The cosmic horizons give these abstract questions concrete form. There really are regions of the universe that can never be observed. Not because of technological limitations, but because of fundamental physics. What we say about these regions reflects our deepest assumptions about the nature of reality. But there's an even deeper philosophical puzzle that arises when we consider the possibility that the universe is infinite. This is called the measure problem, and it strikes at the heart of how we reason about our place in the cosmos. If the universe is infinite, and if it's roughly uniform on the largest scales, then it contains infinitely many galaxies, infinitely many stars, infinitely many planets. And if the laws of physics are the same everywhere, then every possible configuration of matter occurs somewhere. Not just once, but infinitely many times. This includes configurations identical to Earth. In an infinite universe, there would be infinitely many planets exactly like ours, with infinitely many copies of you listening to these exact words. Not metaphorically, literally. An infinite universe contains infinite copies of everything. This is a genuinely disturbing conclusion, but it follows logically from the assumption of an infinite uniform universe, and it creates a profound problem for reasoning about probability. Suppose you want to ask, what is the probability that a randomly chosen observer lives in a galaxy like the Milky Way? In a finite universe, you could, in principle, count all the observers and calculate what fraction live in Milky Way-like galaxies. But in an infinite universe, there are infinitely many observers in Milky Way-like galaxies and infinitely many observers in other types of galaxies. Infinity divided by infinity is undefined. The probability is meaningless. This might seem like abstract philosophical hair-splitting, but it has real implications for cosmology. Many questions cosmologists want to answer involve reasoning about what's typical or expected. What should we expect to observe given our theories? How likely is life to arise in a universe like ours? These questions become paradoxical in an infinite universe because typicality becomes undefined. The measure problem has no agreed-upon solution. Various proposals exist for how to compare infinities and define probabilities in an infinite universe, but none is universally accepted. Different measures give different answers to the same questions. This uncertainty infects our most basic reasoning about the cosmos. We want to know if our observations are typical, if the universe we see is representative of the universe as a whole. But if the universe is infinite, these questions might not have well-defined answers. The measure problem reveals that our conceptual framework struggles not just with distance, but with the very logic we use to think about an infinite cosmos. The universe might be so large, so strange, that our usual ways of reasoning simply don't apply. Distance is just one casualty of this conceptual breakdown. Probability, typicality, and existence itself become problematic when applied to infinite spaces. In our everyday experience, distance has certain properties we take for granted. It implies potential accessibility. If something is a certain distance away, you could, in principle, go there. You could observe it, interact with it, affect it, but cosmic distance doesn't carry this implication. Things can be a certain calculable distance away and still be completely unreachable. The distance is real in some mathematical sense, but it doesn't correspond to any possibility of interaction. What good is a distance measurement if it tells you nothing about reachability? If two objects can be calculated to be 20 billion light years apart, and yet be completely unable to affect each other, what does that 20 billion light years really mean? The answer, increasingly, is that it doesn't mean much. It's a number we can calculate, but it doesn't correspond to our intuitive notion of distance. It doesn't tell us how long a journey would take, because no journey is possible. It doesn't tell us how long a signal would take, because signals can't arrive. It's a number without practical meaning. This is why astronomers have increasingly moved away from using distance as a primary descriptor for distant cosmic objects. They use redshift, which tells you about the expansion factor since the light was emitted. They use look-back time, which tells you how far into the past you're observing. These quantities are directly related to observable properties of the light we receive. Distance, by contrast, requires additional assumptions and interpretations. It depends on which definition you use. It doesn't correspond to any observable property of the light. It's a derived quantity, calculated from observations using models, and different models or definitions give different answers. When you look up at the night sky tonight, you're looking at objects whose distances range from completely unproblematic to philosophically fraught. The moon is about 1.3 light seconds away. That's a straightforward distance in every sense. We've sent people there. The distance is fixed and measurable. The planets are light minutes to light hours away. Still fairly straightforward, though communication delays become noticeable for spacecraft missions. The stars are light years away. Distance starts getting complicated here because we're seeing them as they were years ago, but the distances are stable enough to be meaningful. The nearby galaxies are millions of light years away. We're looking millions of years into the past. The distances are well defined, but the objects have changed since emitting the light we see. The distant galaxies, the ones visible only through telescopes, are billions of light years away by some measures, different numbers by other measures. Their distances depend on which definition you use. Many are approaching or already past the event horizon. Communication with any civilizations there is impossible. Beyond all of this is the universe we cannot see. Beyond the particle horizon, beyond the event horizon. Regions that exist, presumably, but for which distance is simply undefined in any practical sense. This gradient from meaningful distance to problematic distance is the story of modern cosmology. As we've looked deeper into the universe, we've watched our most basic concept gradually lose its grip. Some people find this disturbing. The universe seems less comprehensible, more alien, more strange. We can't even describe it in familiar terms. Others find it exciting. The universe is more interesting than we thought. There's more to learn, more to understand, more ways that reality surprises us. The breakdown of distance isn't a failure of understanding. It's a triumph. We've understood enough to recognize the limits of our everyday concepts. I find myself in the latter camp. The fact that distance becomes problematic at cosmic scales is one of the most fascinating discoveries about the universe. It reveals something deep about the nature of space and time. It forces us to develop better concepts, more adequate tools for understanding. It shows that reality is richer and stranger than we could have guessed from our everyday experience. The universe doesn't owe us simplicity. It doesn't have to be describable in the terms we find intuitive. The fact that it exceeds our intuitions, that it requires new concepts, that it breaks our familiar frameworks, this is what makes it worth studying. So the next time you contemplate the night sky, remember what you've learned. Those points of light are connected to you by something we call distance, but that word means different things at different scales. Some of those connections are straightforward, others are complicated by expansion and redshift. Still others are severed entirely by cosmic horizons. The universe is vast, but more importantly, it's strange. The space between things isn't the simple emptiness we imagine. It's a dynamic, expanding, possibly curved, possibly wrapped structure where distance itself becomes problematic. We live in a cosmos where the simple question, how far away is that eventually has no good answer, where the space between things grows moment by moment, where horizons limit what we can ever know, where the familiar concepts of everyday life break down at the largest scales. This is the universe we inhabit. Not a simple container with objects at various distances, but a complex evolving structure where our most basic concepts fail. And perhaps that's the deepest lesson. The universe is not required to fit our concepts. We have to expand our concepts to fit the universe. Distance worked for millions of years of human experience. It works for navigating cities and countries and even solar systems. But it doesn't work for the cosmos as a whole. The universe is bigger than our concepts, and when distance fails, we have to find new ways to understand. Thank you for joining me on this journey to the edges of meaning itself. The next time you look up at the sky and wonder how far away the stars are, remember that the answer is more complicated than any number could capture. Distance works until it doesn't. And at the edges of everything, it doesn't. Good night. Sleep well knowing that you occupy a small point in a vast universe. A universe so strange that even the space between things defies our understanding. The distances to the stars are real in a sense, but also provisional, changing, multiple, and ultimately, at the largest scales, without clear meaning. That's not a failure of knowledge. That's the universe revealing its true nature. And that nature is more wondrous than simple distances could ever convey.